Hi, I'm Meghna Sitaram. This summer I worked with Felix, he's right over there, on detecting torsional modes in tapered nanofibers. So I'm going to explain a little about what that means. So we make these tapered nanofibers from regular optical fibers, the same type you use for internet, for example. And these optical fibers are made of two concentric cylinders of glass with different indices of refraction. So there's the core, which has a slightly higher index of refraction, and it's usually about on the order of 10 microns in diameter. And there's the surrounding cladding, which is usually about 125 microns. And to make the nanofibers, we heat and kind of soften the fiber and stretch it out until the center region, the nanofiber region, and the diameter of the nanofiber region is about 0.4 to 0.8 microns, or 400 to 800 nanometers. And the structure of the nanofiber, or the tapered optical nanofiber, includes, so it starts off with the regular optical fiber, and then there's a linear taper with a constant angle, and then at the very end, right before the nanofiber region, kind of right there, there's a small exponential taper before there's the nanofiber region. And one really cool thing about these optical nanofibers is that the nanofiber region is actually sub-wavelength. So the light will travel outside the fiber and kind of rejoin back into the fiber at the end of the nanofiber region with very little loss. And that's kind of because in the nanofiber region, the core region kind of disappears, and your cladding, or the material of the cladding, is like the new core of the nanofiber, and your vacuum is like your new cladding. So that's one of the reasons that nanofibers are super interesting, and also we would like to use these nanofibers to generate correlated beams of light and maybe classically squeezed light, which has lots of applications in quantum metrology and optical communication. So the way we make these nanofibers is with a motorized pulling apparatus. So the nanofiber is represented by this line over here. So we connect it to two motorized stages, and they kind of slowly pull apart. And the whole time, this pure hydrogen-oxygen flame is heating it, and we had to make sure that that was a hydrogen-oxygen flame whose only byproduct is water, because we could not have a flame that would deposit any residue on the fiber. It's extremely fragile while it's being pulled, so even one speck of dust could cause it to be damaged or broken. And the whole time, we have a reference laser traveling through the fiber and a detector. So we monitor the transmission and make sure that the fiber hasn't broken or isn't damaged. And usually we have a pretty good transmission of about 97%, so like 3% loss caused by the pull, and sometimes we have even less too. And here you can kind of see an example of what a nanofiber would look like. And you can see how the end kind of tapers off into nothingness. And that's the nanofiber region, because it's way too small for you to be able to see. This one's actually broken. This is the very first nanofiber we tried to pull. And if it were still whole, it would be going straight across the other end of the mount. But our second one is good. It's still alive, so yeah. And there are two types of mechanical modes that you can have with these nanofibers. There's your classic jar string mode, which is kind of like a standing wave, and those are very low frequency. And the ones that we're interested in are the torsional modes, which is kind of like the twisting motion that you can see over here. And those happen at around 150 to 200 kilohertz, depending on the physical properties of the nanofiber. The way that we detect the torsional modes is using a technique called heterodyne detection. And this involves mixing a high-powered, frequency-shifted local oscillator with the signal. And what this does is the local oscillator basically amplifies the signal and brings it and increases the signal-to-noise ratio. And it kind of brings it above electronic noise so that we can see any weak signals and they won't be hidden from noise from the detector. In addition, they shift the frequency away from low-frequency noise just from the environment that we can't get rid of. And if heterodyne detection is done correctly, then we'll be able to see a peak on the spectrum analyzer at the frequency difference that we chose. So for our purposes, we used 1 megahertz. And this is what we would see on the spectrum analyzer. So on the y-axis, we have the power in dBm, and on the x-axis, we have our frequency in hertz. And you can see that we have our beat note at 1 megahertz there. And you can also see that the noise floor of the local oscillator is above the electronic noise floor, so we would be able to see any weak signals. And here is what we'd see on the spectrum analyzer after we detected the torsional modes. So it's the same thing with the power in dBm on the y-axis and the frequency in hertz on the x-axis. And we know that we're seeing torsional modes because we see our sidebands at 160 kilohertz just about. And basically what this means is the negative sideband kind of means that the light is driving the torsional mode, and the positive sideband kind of means that the light is receiving a frequency kick from the torsional mode. So our future goals, well, first, after the summer, we now have a fiber pulling setup. So I forgot to mention, me and Felix actually helped rebuild the fiber pulling setup after it was moved into a different room and kind of taken apart over the summer. So after the summer, we now have the ability to create new nanofibers with the parameters of our choosing. And we also created the heterodyne detection setup. So we now can excite and detect these torsional modes and try new nanofibers. And our future goals include testing whether these two bands of light, the side bands, are correlated, and if they are, perhaps try to generate classically squeezed light. And if you were wondering what our setups looked like, here's the fiber pulling apparatus, and you can kind of see the two motorized stages here and the flame in the middle. And here's the heterodyne detection setup, and those two huge silver things are the two vacuum chambers with the nanofibers. And I would just like to quickly thank Bonnie, Paul, Kevin, and everyone else in the lab. Thank you so much. Okay.